Now let's talk about another way of modifying graphs, which is vertex and edge operations. So this is just a couple of ways of adjusting the vertices and edges of a graph, and we'll give a nice application of them to prove Euler's formula, which is a very nice result about planar graphs. But we will get to all that. So given a graph G with a set of vertices and a set of edges, we can produce a new graph in a number of ways. Here are some ways that we can do it. We can remove an edge. So, for example, we have a graph like this. We can remove this edge to get this graph. Same vertices, but with one less edge. Or we can do something, we can add an edge. So for example, the graph we ended up with here, we can add an edge, say this diagonal one, to get a new graph looking like this. So this is basically just, changing the edges of your graph, but doing it in a controlled way is often useful in making arguments about graphs, as we'll see in our application. There's also a slightly more complicated way that you can adjust the edges, in fact, which adjusts the vertices and the edges, which is to contract an edge. So instead of just disappearing the edge, like we did in this case, contracting an edge means remove the edge and replace its two endpoints with a single vertex. So you're sort of taking the edge and you're squishing it down to a point. So if we do this same example, and we contract this edge instead of removing it, what we get is, so this edge disappears and these two vertices become a single vertex. And they remain connected to the vertices they were connected to before. So we get this. And as another example, let's say we have some graph like this, and we contract this edge. So now we have these three vertices like before, and these two vertices become a single one. So it's going to look like this. And then, so these vertices were connected like this before. And this vertex, we don't worry about doubling any edges that were present for both vertices. We just make sure that it's connected to all the same vertices that it was connected to before by a single edge. So these two edges become this one edge, and these two edges become this one edge, and then this edge becomes this edge. So that is what we get when we contract an edge. And in addition to these edge operations, we can also do the same kind of things with vertices. So we can remove a vertex from our graph. And if we remove a vertex, we have to remove all the edges connecting to it because they no longer have endpoints. So we have this same graph that we have there, and we remove this top vertex, then we have all the 4 remaining vertices, and we have all the remaining edges that were between just these vertices. So it looks like this. So we deleted this vertex, and we also deleted all 4 of the edges coming out of that vertex. And in addition to removing a vertex, you can add an isolated vertex, which, again, doesn't do anything special. You just have the same graph, but now it has an extra vertex. And maybe if you wanted, you can add some edges in. But again, it's just good to have these basic moves that you can do to manipulate your graphs. So let's see an application of these ideas, which is Euler's formula. So Euler's formula is a formula about planar graphs. So first, we need to define what planar means. A graph is planar, meaning like planar as in the plane, if it can be drawn in the plane without any edges crossing. And such a drawing is called a planar representation. So let's see some examples of this. K3, so remember that Kn is the complete graph on n vertices. So K3 is a triangle. And this graph is visibly drawn with no crossing edges. So this graph is planar. And even it is currently drawn in a planar representation. K4 is the complete graph on 4 vertices. So this graph, you can see, has an edge crossing, but that doesn't mean that it's not planar. What that means is that this is not a planar representation. So a planar representation is a drawing where no edges cross, but a graph is planar if there exists a planar representation. And in this case, there does, because we can take this line, this edge, and bring it outside to keep it from crossing. So, but here is another way of drawing it that is a planar representation. No edges crossing here. So K4 is planar. And K5 this is evidently not a planar representation, because you can see we have a bunch of edge crossings going on in the center here. And in fact, it can be shown that K5 is not planar at all. So there does not exist a planar representation. But this is not obvious. That requires a proof. So now that we know what a planar graph and a planar representation are, we can state Euler's formula. Which says in a planar representation of a connected graph, so we're going to talk more about connectivity tomorrow, but for now, connected just means that it's in one piece. So in a planar representation of a connected graph, we have v minus e plus f is always equal to 2, where v is the number of vertices, e is the number of edges, and f is the number of faces or regions that the plane is divided into. By the planar representation of our graph. So just to illustrate this with an example, let's do the example that we gave up there. So for this graph, how many vertices? There are 4. How many edges? There are 3, 4, 5, 6. 6 edges. And how many faces, or how many regions, is the plane divided into? Well, there's this one, this one, this one, and we do include the outside region, outside of the whole graph. So there are 4 faces. Well, let me erase that. So there are 4 faces of this graph, and we see that 4 minus 6 plus 4 is indeed equal to 2. So Euler's formula checks out in this case, but the claim is that this is true for any planar representation of any planar graph. And this is a beautiful result because, I mean, first of all, it's just a very nice, simple relationship that these different facets of a planar graph have to satisfy. But also, it is a very nice example of some deep ideas in geometry. If you think about it from the perspective of each of these quantities, you are sort of adding up the information about your graph coming from each of the different dimensions. So the vertices are the 0-dimensional pieces, and the edges are the 1-dimensional pieces, and the faces are the 2-dimensional pieces. And this formula is giving you some relationship between how, the properties of your object in each different dimension. And this is a very powerful idea in geometry. And in fact, that's, one way of pitching a vague idea of my own research is that the thesis project that I'm working on is to compute some kind of very fancy Euler formula in some much more technical setting. But it's exactly along the same lines. It's just like some kind of like massive generalization of this idea. So let's prove this. And we're essentially going to prove this by using our vertex and edge operations to adjust our graph in a way that does not mess up this formula. So here's a proof. So start with a planar representation, which we are given in the statement. So starting with a planar representation, we start by adding edges so that each face is a triangle, meaning that each face is bounded by 3 edges. So for example, well, let's take an example that will walk through this entire proof. So here is a planar graph drawn in a planar representation. And all of the edges, all of the faces are triangles, except this one. So we just want to add an edge to make that a triangle. So we just add that this last edge in here to make that 2 triangular faces. And we don't worry about the outside face in this step. In this case, it's got 4 edges bordering it, but we don't worry about that one. We don't need it. So let's be careful, because we're modifying our graph, and we want to know what happens to our formula when we modify it. And so what happens when we do this? Each new edge, so it increases the number of edges by 1, because we drew a new edge, and it increases the number of faces by 1, because we have taken a face and divided it into 2 faces. So that increases by 1 as well. And the number of vertices does not change, because we only added edges, no vertices. So each new edge increases E and F by 1. And since we are taking this sort of alternating sum, E is negative and F is positive. So V minus E plus F stays the same. So the idea is that we don't know this formula yet, but we're going to keep doing these operations that don't change the left-hand side until we can simplify it to something where it's clearly equal to 2. So the first step is to divide all the faces into triangles. Then we repeatedly apply either of the following 2 steps. So the first possibility is remove an edge from a triangle. If the triangle has a single edge on the boundary. So in the current status of our example, this triangle here, this right-hand face, has a single edge on the boundary, which is this one. And so we can delete this edge to get a new graph that looks like this, like that. So we're just deleting this edge. And what does this do? This decreases E by 1 because we're deleting an edge, and it decreases F by 1 because we are taking 2 faces and joining them into 1 face. So again, V minus E plus F, since we're subtracting 1, or we're adding 1 right here and we're subtracting 1 right here, this stays the same. And the other thing we can do is remove a vertex from a triangle with two edges on the boundary. So in this example, we can, for example, this triangle on top now has two edges on the boundary. So we can go ahead and delete this hanging vertex to get this graph. So we delete this vertex and the two edges connecting to it. And what happens when we do this? It decreases the number of vertices by 1 because we deleted a vertex. It decreases the number of edges by 2 because since this is a triangle with two edges on the boundary, there are two edges that are going to disappear when we delete this vertex. And it decreases f by 1 because, again, we're taking these two faces and joining them into a single face. And again, if you do this counting, we're subtracting 1, and adding 2. So in the end, v minus e plus f stays the same. Okay, so we started with this graph, and we've gotten it all the way down to here. And so using these maneuvers, we can always reduce our graph to a triangle. So we are currently in this situation, and you can see that all we need to do is another of the second kind of step, removing, for example, this vertex from the triangle, which has two edges on the boundary. And what we get is a triangle. Now, vertices minus edges plus faces for a triangle, since we've reduced it to a specific case, we can just compute it out. It has 3 vertices, 3 edges, and 2 faces, which is 2. And looking back at everything we did, ooh, wow. Since we started from any planar representation of any graph, and we did a bunch of maneuvers that never changed v minus e plus f, this quantity v minus e plus f stayed the same throughout the entire process. And at the end, we found that it is equal to 2. So it must have been equal to 2 all along. That completes the proof of Euler's formula.